Hello again, and welcome back to Resonance Basics. This is going to be part 2 of our video talking about resonance. We've already gone over the basic rules, what resonance means, and we've gone through example 2 in part 1. But now we're going to go through these other 2 examples, and then after that, we'll see about talking about resonance hybrids and stability of resonance forms. So now that we're done with example 2, remember example 2 came from moving the lone pair here on the nitrogen to the bond. So then it looks like this. So let's look at example 3. So example 3, we're going to go through the same process that we did before. We've already got it in expanded form because you already wrote that down. So let's use this form first, and then I'll show you how to go back to the line bond form. So if I look here, where are my extra electrons? So for this example, I actually have a choice. I have a lone pair and I have a double bond. So I'll give you a tip. If you ever see this problem, always start with lone pairs. Look for those first. Lone pairs negative charges are the most important. Then if you can't find them, then go to the double bonds. If you have a lone pair, start with that. Don't start with the double bond. Because as we can see down here, double bonds are also a place electrons can go, and I'm going to show you how that works. So the place that we're going to start is going to be from the lone pair on the oxygen. It doesn't matter which one, they're identical, so you just pick one, you're only going to use one. And then we're going to move that. So where is the place where electrons can go? Like I just said, they're going to be in the multiple bond, in the double bond. So let me show you how that works. So we're going to take these electrons here and move them to make a double bond. So we're not going to jump around. We're going to go move to the bond. So put those there. And then we're actually going to have to do something else. Because if we don't, if we leave that and make that a double bond, the carbon would have 2 double bonds and then a hydrogen, and that'd be 5 bonds. That's against the rule. So anytime you move electrons towards a double or triple bond, you're going to have to then move another arrow where you move the electrons away from where they were. So now I'm going to move this double bond away and put it on the carbon, like that. So that's what my arrows would look like. So then what would my actual structure look like? Let's draw that. So remember, the first step we're going to do is to draw all the single bonds, so all the single bonds over here. And then I'm going to draw where my arrows did. So now my arrows, they moved this to make a double bond, and then this double bond went away. And then that moves, if that double bond goes away, those 2 electrons, where'd they go? They went to make a lone pair on the carbon, so now they're right here. So those 2 electrons from the double bond over here are this lone pair right here. So hopefully that makes sense. This also means that I'm going to have, on the oxygen, I should have 1 lone pair left over. One of them moved to make the double bond, but the other one's still there. Again, it doesn't matter if it's the top or bottom one, I'm just going to draw it like this. Alright, so the next thing that we're going to do is, after we have drawn all the atoms, we've drawn where the electrons move, the last thing we want to do for the structure itself is to show if there's any formal charges that have changed. So if you look on the structure on the left that we started with, that was neutral to start with. If we start moving electrons around, the formal charges should change. That should happen. So we'd expect that. So let's look and see where things might have happened. So obviously the only changes are going to be where the arrows are. So we're either going to have a change on the oxygen, the middle carbon, or the right carbon. So let's look at the oxygen first. So if you look at this oxygen here on the structure on the right, that's going to have a formal charge of what? It's going to be 6 minus 3 minus 2, which is plus 1, right? So then if we look at the middle carbon, in the middle carbon we've got 4 bonds, so that's going to be a formal charge of what? 0. And if you look at the structure on the left, it was also 0, so that actually didn't change. That should make sense because if you look at the curved arrows never touched that middle carbon. They just sort of went around it, so they only changed bonds. They didn't change anything into a lone pair. So that should be normal. So then if we look at the carbon on the right, that's the last one. For the structure here, it's going to be 4 minus 3 minus 2. So what would that formal charge be? Correct, it's going to be minus 1. So we should have a charge of plus 1 on the oxygen and a charge of minus 1 on the carbon all the way to the right. So now that we've got the structure, let's go ahead and convert that to line bond form. So I'm going to do that over here on the left. Go ahead and pause the video and try that. Hopefully you got a structure that looks like this. So remember, with line bond you don't need to show the lone pairs, so I just showed the charges here on the oxygen and the carbon. And then make sure that you have the right number of carbons. That's a good last step. So if I count the carbons on the structure on the right, I've got 1, 2, 3, 4, 5. If I count the carbons on the structure on the left, I've got 1, 2, 3, 4, 5. So that means that they match, which is a good sign. So now I've got one more resonance form. Now the next question is, can I move it any further? If I look at the structure on the right, the lone pair is what I would be moving. Can I move that lone pair any further to the right? The answer is going to be no, right? If I move it to the right, there's a carbon with 3 hydrogens already, and that would make a double bond, and we already saw that's not okay. So then I know I can't go any further to the right. Can I go any further to the left? Let's go back and look at the original structure with the 2 lone pairs in the oxygen. Can I move one of these lone pairs over to the left carbon or to make a double bond? No, right? Because if I did, again, I'm going to end up with 5 bonds to carbon. Carbon already has 4 bonds, and so I can't take anything away. I can't move the single bonds. So I can't go any further to the left. So if I can't go to the right and I can't go to the left, then I'm done. So the last thing I'll do is label my structures. This will be A, and this will be B, and then that example's done. So hopefully by now you're starting to get the hang of the resonance structures, but let's go through one more example just to make sure that we've got it. So now let's look at example number 1. So I saved the slightly longer one for last. So what we're going to do is we've already drawn the expanded form. As you can see down here, I just moved it so we had a little bit more space, and we're going to move the electrons around. Now in this example, hopefully we've kind of gotten used to the different types of forms. So I'm actually going to move the electrons around on the top form. I just wanted to have this other form available so you can sort of see where things are. So it sort of is a reminder. So we're basically taking out one of the steps, and hopefully you'll be able to do that on the test, so you will always have to draw these. All right, so the first thing we're going to do is look for where the electrons are. So in this molecule, the only extra electrons that we have that can move around are in the double bonds. We don't have any lone pairs, we don't have any negative charges. So that means they have to be in these double bonds that we see here. So then where are places that electrons can go? Right, so here I've got a positive charge. That would be the most obvious place that electrons can go. I did say that electrons can move to double bonds, and that's totally fine. We're going to always, if we have a positive charge, start with that one first. Just like if we have a negative charge, we'd start with that first. So always start with the charges, and that will give us a clue of where to begin. So let's draw an arrow from a double bond that can move to the positive charge. So which one is that? Not all of them can move there, right? Right, so only this double bond here can move. So let's have that move from here, and it can't jump all the way over to the carbon. It's going to go from the bond to the bond. So that means we're going to move the double bond that was on the left side of this carbon to the right side of that carbon. We're not going to have it jump and make it a lone pair, because it can't do that. That's not allowed. Now in this case, do we need another arrow? No, because it's going to fill that positive charge. It actually has a space that's open. A carbocation only has 6 electrons. It wants those electrons. So you can move that there, and you don't have to move anything away like you would if you were moving it towards a double bond. So the next step is we're going to draw our structure. So first I'm going to draw all of the single bonds, and in this case I'm just going to go with the line bond. Here is what it would look like. So that's all my single bonds, but I've also got some of the double bonds that didn't move, so I'm going to draw those in as well, anywhere where there's not an arrow. So now I can draw where my arrow actually moved the electrons. So to do that, I'm not going to draw the double bond, but I'm going to move it over to this carbon on the right, so right there. So now I need to check the charges. So I know I should have a positive charge because the overall charge of the molecule shouldn't change, and I started off with a positive. So where's my positive going to be? Well, if I look at the structure at the bottom, I could figure it out doing formal charge. But just looking at the top, I can tell based on the arrows. The arrows are always moving electrons away. So anywhere you move the electrons away from, it should become more positive. And anywhere you move the electrons to, it should become more negative. So if this moved over here, it's actually going to leave a positive on the carbon that it left behind, right here. And if you look at the carbon in the bottom structure, that would be this one here. Imagine that double bond's gone, that would be a positive charge, right? And then it came over to this side, so that means where there was a positive, that's now going to be neutral, because a plus a minus, because more negative, means that it's going to be 0. So now there's no charge on this carbon. So again, if I look at the structure on the bottom, if imagine I put a double bond there, then that would be a neutral because I'd have 4 bonds. So it's just an easier way so you don't have to keep doing the math every time. All right, so now that structure's done. The next thing I'm going to do is see if I can move anything else. So obviously I don't want to move anything to the right of that positive charge because that'd be going back where I started. So let's look on the left. Are there any electrons that I can move towards the positive? Yes, there actually are. So I can move this double bond here to the right and move the double bond over to fill that positive charge. So let's do that. So what would that structure look like? So let's draw all the single bonds again, like this. Then we will add our extra double bonds that didn't move, so now I'm not going to move the one on the right, and I'm not going to move the one down here. Then I will move the double bond to put it here. And then where's my positive charge going to be? Right, it's going to be on this carbon down here where I moved the electrons away from. Notice there's no double bond there anymore, so I've got to put the positive on that carbon. So now, can I move anything else? Again, keep going around the ring. Can I move that double bond there? Yes, I can, so let's do that. So this time, go ahead and pause the video and draw the curved arrow of where you think it should be. Hopefully you got this. Now, if you got that arrow, what structure would that look like? Remember, you're going to draw all the single bonds first and then move stuff around. So pause the video and try that. All right, so hopefully you got this structure. If not, you can always ask me questions, but this is the correct structure, so I've moved the double bond here, and I've left the positive charge over here. So now let's see if there's anything else we can move. So I actually see one more double bond that can move to the positive charge. Do you see it? Right, it's right here. So we can move that double bond over here with this curved arrow. So I want you to draw what that structure would look like. All right, hopefully you got this. So we just moved the double bond just the way we always have been, and we ended up with a positive charge here. Now looking at this structure, you might be thinking, hey, that looks familiar. Is that the same as the structure that we started with? So let's look at it. They both have 3 triple bonds in the ring, and they both have a positive charge. But what's different about those two? Right, the double bonds are not in the exact same spot. So even though they're equivalent, right, they would have the same number of double bonds, they're not in the same spot, which means that they're separate resonance structures. So then the last thing we do is see if we can move any of the other structures around. So we can't, right, because we're back to where we started. We can't move anything onto the carbon on the right. And remember, that's because it has 3 hydrogens already there, so that's already used up. So there's no way we could have taken, say, this middle structure and moved the double bond over there. That would not have worked out because we would have had 5 bonds. So now, since we're done, we'll just label these. This will be A, B, C, D, E. And as it shows, we would have 5 structures total for this molecule. Now, you'll notice this ring with the double bonds in it, you're actually going to see that again. Anytime you see a 6-membered ring with 3 double bonds inside it like this where they're alternating, that's called an aromatic or a benzene. So anytime you have an aromatic with something in the carbon right next to the aromatic, that could be a lone pair, that could be a negative charge, or that could be a positive charge. If you have those 2 things, then you're always going to have at least 5 resonance structures, usually only 5 in this class. All right, so now we're done with all of our examples. The next thing that we would talk about is the most significant contributor to the resonance hybrid. So really that's going to be the question of what form is the most stable. So A or B or A through E in the last case, which of those is the most stable? Then after that we can talk about drawing the resonance hybrid, which is not too complicated, but something that you'll also want to know. These are topics that I plan to make a video on, but I may or may not have gotten to that yet. So check Blackboard, and if you don't see anything, we'll just cover it in class. And if you're following me on YouTube, just stay tuned. I hope everyone's having an awesome day and having a great time learning organic chemistry. Catch you next time.